So I want you to please welcome the biggest Rangers fan you'll ever meet, Wilson Cauley.
Thank you, Dan, very much. I'm very excited to be here. Thank you for inviting me. I'm a big Rangers fan, but I spend most of my time doing my job, which is studying exoplanets. So I know we have a lot of people who are very familiar with astronomy in the crowd, so later on in the talk we're going to get pretty detailed and we're going to talk about what I actually do for research. And I like it better if you ask questions when you have them instead of waiting until the end, because I tend to forget my questions. So just ask them, put your hand up and we'll call on you and we'll ask your question. So the title of the talk is Planet or Star, Understanding Spectroscopic Signatures of Transiting Exoplanets. And a lot of this has to do with stellar activity, and we're going to talk about that with the sun as an example, and then how that applies to other stars. And my work in particular is focused on trying to look through the atmospheres of extrasolar planets as they transit their stars. And we'll talk about how we do that. So just a little bit of background and perspective. I put this number up. There's now 3,000 plus confirmed exoplanets around other stars. That number changes every day, and different websites give you different numbers that you're going to see. So the bottom line is there's tons of them, and we're finding them all the time. There's lots of teams looking for these exoplanets. A lot of amateur astronomers go and do follow-up. They do transit timing stuff. So I encourage you, if you're interested in exoplanet observations, to go look at some of the stuff you can do with your own telescopes in the backyard. It's pretty amazing. So this is cool that we're finding all these planets, but the really interesting thing is now, based on all of these surveys that have been done, we have pretty good statistical evidence that there is at least a planet around every star in the galaxy. At least one. And that's sort of like a rough number. And if you're a scientist and you like science and you believe that it works, then you probably believe that the physics in our galaxy is very similar to the physics in almost every other galaxy in the universe. So what that means is there's probably a planet around every other star in the universe, not just in our galaxy. So that's a pretty incredible statement, but maybe not surprising, right? Because if physics operates the same way and we get the same processes happening around all stars, we probably get planets around all stars. So it's very exciting, it's very interesting, but it's also sort of this inevitable process of star formation. Planets are like the leftovers that form in the disk around the star. All right, so how do we actually do this? How do we find exoplanets? Well, there's two main ways. And I'm sure a lot of you have heard of these methods. One is the transit method on the left. The planet goes in front of the star. You see the star dim a little bit, and you can measure the brightness change, and that gives us the relative size of the planet compared to the star. The other method is called the Doppler shift or the Doppler wobble. And this is a little more in depth, and you don't necessarily need the planet to be transiting. And what you're measuring is a shift in the spectrum of the star as the planet tugs on the star, and it moves back and forth relative to our line of sight. And I work with spectra, so I like the RV method. I think it's really cool. It's more general. You don't need transits to find planets. But this gives us the mass of the planet. So these are complementary methods. And if you have a transiting planet, you can go and follow up with the RV method, and you can get a mass. That lets you do cool things like find out the average density of the planet or something like that. So these are our two main methods for finding exoplanets. This is just to give you a little bit of demographic background information. So this is a plot that shows how long it takes the planet to orbit on the bottom versus how big the planet is in Earth radii. And the green Earth symbol shows where Earth is on this diagram. So you can kind of see, and I'd look at the blue, I wouldn't look at the red ones yet. Those are things that have not been confirmed as planets yet, but they're high probability. So you can see we haven't really probed the place where Earth is that much. That's really hard to do. And we'll get there eventually, but the long time scales and the very small transit probabilities make it very difficult to detect planets out there. But you can see we've detected them almost everywhere. So my work mainly focuses on this kind of special region which we call hot planets. And they're hot because they're really, really close to their host stars. If you look at the x-axis, you'll see they orbit within 10 days of their host star. Whereas we take about 365 days, these planets go around once every 10, once every 5, even less than a day. So they're super hot. They're like 1,000 to 2,000 degrees, very, very hot surfaces. But what this does is it lets us study some really interesting physics that goes on in the atmospheres of these planets. They get really puffed up and big. They can lose a lot of mass. And so we're able to observe these more easily than we can a lot of the stuff out in the other exoplanet parameter space. So keep that in mind. These are the guys that I'm going to be talking about. And hopefully Franco will like this. So what I'm going to talk about has a lot to do with what the star is doing. It's not necessarily what the planet is doing. And we really only know the stuff about the planet as well as we know the stuff about the star. So if you looked at the sun, if you're able to just look up at it with your eyeballs, don't ever do that, but if you could and it was a lot dimmer, you'd see something like this. This is basically a white light image. And you'd look at it and say, it looks pretty homogeneous. There's not a lot going on the surface of the sun. You see some spots, but for the most part, it's pretty much the same everywhere. But we know that's not true. And what you can do is if you look at other wavelengths of light, we see crazy differences across the surface of the sun. And it changes with wavelength. So if you go really far into the ultraviolet, you can do things like this. This is from the Solar Dynamics Observatory. And you see the corona, you see this really extended atmosphere that's out above the sun. You see these really bright features in these magnetic loops in the chromosphere. And down here you see a coronal hole. This is like a much lower density region of the corona that's very faint, and you get a really strong solar wind coming out of there. So we have all these different things going on, and this is really important. So what we see depends on what wavelength of light we're observing it. And the same is true for other stars. So just a couple more examples. I'm going to emphasize the fact that the sun is special because we can actually see what's on the surface of the sun. Keep that in mind. Every other star that we look at, what you're doing is you're taking all of the light and you're throwing it together and mixing it all up. We have no idea where on the surface of the star that light comes from. We can reproduce models that give us rough estimates, but we can't spatially resolve other stars. The sun is the only example that we have that we can do that. So you can also see another example on the bottom right. If you watch the sun over a whole rotation period, you have these concentrated regions of activity on the surface of the sun. These are latitudinal bands, and they drift with time. They change depending on the sun activity cycle. So when we look at the sun, we have to extrapolate, and we say, we probably have things like this on other stars. Granted, the magnitude of these changes can differ from star to star, but we generally believe, and we know from some empirical evidence, that you do have things like coronal prominences on other stars. You do have things like star spots. We can actually see that happening. We do have activity bands. We can watch those change on other stars. The methods are more indirect. We're not taking pictures like this. But we have pretty good evidence. All right. So, another thing is changes in time of the stellar activity level. The last slide was just images, but on the left here, we have a video of the sun, and I think this is from 2015. And if you watch in the upper left corner, you'll see a really quick brightening. So this is a whole day, so this probably happens over the course of minutes. And you'll see it get really, really bright, and it basically saturates the camera that's taking the image. This is a stellar flare, or a solar flare in this case. But we see this on other stars. We see solar flare or stellar flares all the time. On the right, this is Kepler data of an M dwarf, and we see these really sharp increases in brightness, which is the y-axis, and then it kind of tapers off slowly over time. And on the bottom, you can see one where it had like multiple flares, one after the other, and they are able to see a bunch of these peaks. So this is another aspect of other stars that we have to keep in mind. They not only have these surface features that are change as a function of where it is on the disk of the star, but they can vary in time. So this is another variable you have to keep in mind when you're looking at this stuff. What does this mean for our detection methods? Well, when planets transit stars, they don't always transit the pure photosphere, right? They can transit these active regions and these spots. And what that can do is it can change your transit curve. And when you're covering a spot, since the spot is fainter than the rest of the surface of the star, you're essentially blocking less of the total light that you're observing from the star. This causes an decrease in your transit depth. So it makes the planet seem like it's smaller. And if you transited a bunch of spots in a row, your transit curve would look a lot different, and you might get the radius of the planet incorrect. So this has implications for the transit method. For the RV method, this is even more profound. All of these little features on the surface of the star give you a different spectrum. So the photosphere and the bright chromospheric regions and the spots, they'll give you slightly different spectra. And not only are the spectra different, but they're all moving around. You have all these little velocities towards us and away from us, and some with some lateral motion. This changes the observed spectra that we measure, and it can have a pretty profound impact on these velocity curves. So if you looked at this and you didn't consider any of the stellar activity, you would say, oh, this doesn't really look like a planet at all. It doesn't
Okay,
look
so
periodic.
slow down a second.
Yeah.
What's the scale on the?
Okay. This is the velocity of the star relative to us, and this is time. These are days down at the bottom. So over time, the velocity changes. And if you looked at this without considering what the star is doing, you would say, oh, it doesn't really look periodic. It kind of looks weird. It gets down here and then it goes up, and it doesn't really look like a nice circular planet going around. If you model what the surface of the star is doing and you throw in a bunch of these spots and these bright regions, you can fit a component that actually gives you a good planetary orbital solution, but it includes all this stellar activity on the surface of the star.
Cool.
So people have to take this into account when they're doing RVs of stars that we think have a lot of this stellar activity going on. And there are other indicators for the stellar activity. You don't get it from the same data.
Would that smooth out over time as you took more and more data?
It can, although a lot of this is periodic. So if you watch the star, let's say the star rotates once every 10 days or something, you see a repeat in these features. They some of them last a long time. So over time, you can build up a general model for how you think the star behaves. Yeah. But you can't always do it perfectly. So sometimes this is not so nice. Yeah.
So it's like predictive resolution
Yes. Resolution. What do you mean resolution?
of what the star is actually doing based
Yes.
on the transition of the planet.
Yep. And people have developed some fairly sophisticated tools that actually result in a distribution of the spots and the active regions. So they can say, it probably looks something like this.
Very cool.
So not only does this have an impact on us finding planets, but stellar activity in general can have a pretty big impact on how the planet evolves. Generally speaking, this is more important for those hot planets I was talking about because they're really close to their stars. So they experience much higher levels of radiation from their stars. So if they're absorbing a lot of energy, they can have their atmospheres puffed up and literally evaporated off of the surface, and they can escape, so they can lose a lot of mass. So you can think of if Earth had existed within a few stellar radii of the sun, it would have had its atmosphere completely boiled off, and it would be just a big rock, and we wouldn't be here. It'd also be very hot. But this can have profound consequences for planets like Earth and Mars. The radiation from the sun, or the light in this case, doesn't have a big impact, but what can have a big impact is the stellar wind. So these are not photons coming from the sun, these are actually charged particles. These are ions and electrons. And they hit the Earth at hundreds of kilometers per second, very, very fast. And they strip away atoms from the Earth's atmosphere. And we think that Mars used to have some atmosphere, at least, and a pretty substantial one. But over time, it was eroded by the solar wind. It was literally stripped away by the particles coming from the sun. So if the star did not have a wind, the planet would be more stable. But most stars have winds, we think. So this is a big problem for planets. Luckily not for ours so far. The other thing, and I'll point this out because it's been in the news recently, Proxima Cen-b is a planet that was recently discovered in the habitable zone of Proxima Cen, which is the nearest star to us, besides the sun. But people have been running some models, and they've figured out that the planet likely had its atmosphere stripped by the wind of the star. It's just too close to the star. So even though it's in what we would call the habitable zone, where you can have water on the surface of the planet, it probably doesn't have an atmosphere because the wind from the star is so strong that it just stripped it away over millions of years. So don't get too excited about Proxima Cen-b having an atmosphere. Probably doesn't. But we don't know yet. Do you have a question?
How come they give us only the good news but not the bad news?
Sorry for that. I'll get to some good news. Okay, so this is one of the things that I focus more on. I'm not going to talk about it too much today, but I thought I'd tell you about it because I think it's pretty interesting because it's not something that happens in the solar system very much. So these hot planets are so close to their stars that we get a lot of weird stuff going on. And a couple of the things that can happen are when the planet is losing mass, some of that mass can be funneled onto the star that it's orbiting. So you can have these stellar flares and activity eruptions that happen because the planet is losing mass onto the star. And one of the ways we look for this is to see if it's periodic. So if the planet's going around and it loses mass every once in a while, or maybe continuously over its orbit, we might be able to detect whether or not the star is having that mass piled onto it. Another possibility is our sun has a magnetic field. Most stars we are able to measure have magnetic fields. These magnetic fields have some sort of area of influence around the star. For these hot planets, they're so close that they are literally inside of that, what we call the magnetosphere. So they interact with the star's magnetic field, and what this can do is sometimes you get these big twistings of magnetic field lines, and they don't like that. There's too much energy, so they like to pop out and go connect with other magnetic field lines. But this releases a ton of energy, and these can be really big flares, and so we try to look at these hot planets and see if we can detect things like that happening around them. And finally, we experience tides on Earth, right, from the moon. The moon pulls on the Earth in closer on the near side, less on the far side, kind of stretches the Earth out. Same thing happens with these hot planets. If you have a massive planet orbiting a star, you can cause tides, big tides on the star, and this can cause variations in the stellar activity level in the outer atmosphere. So how do we do this? What do we use to try to find this stuff? My main tool is what we call a high-resolution spectrum. And I know I've been saying the word spectral a lot, so if you didn't know what it was, here it is. This is called in a shell spectrum, and what this is the wavelength of light goes across the bottom, and we go from blue to red, and all these little black lines are the imprint of atoms in the atmosphere of the star, atoms or molecules. So we take an image of the star and we spread the light out and we get a spectrum. And the resolution tells us how finely we can distinguish between the wavelengths that we're looking at. So high resolution lets us resolve really narrow lines, and low resolution is really just to get an idea of how the shape of the spectrum varies as a function of wavelength. But this is mainly what I use. And just as an example, this big black hole you saw at the top, this is what we call the H-alpha line. This is a really strong hydrogen line in the solar spectrum, and almost all stars that are similar to the sun and much less hot stars and even much hotter stars, they all show this line because hydrogen is so abundant. It's everywhere. So, what are we actually doing? Well, I think I mentioned earlier that what I'm trying to do is look through the atmospheres of these planets and measure some of the stuff that's in there. This is called a transmission spectrum. The light is being transmitted through the outer atmosphere of the planet, and we're measuring a difference between the light in transit and the light out of transit. You can't do transmission spectroscopy if the planet doesn't transit. It's purely a transit method. So this is an example. This is just a schematic showing you what you might see. This is sodium and potassium. So the planet looks bigger if it absorbs at a specific wavelength. So we have a pretty flat slope, and then all of a sudden we have a lot of sodium in the atmosphere. So we see a bigger planet. And this is absorption in the atmosphere of the planet. So this is how we can try to measure the abundance of these atoms and molecules in the atmosphere. It also tells us what's not there. So if we don't see anything, that means we probably don't have a lot of sodium. Or the planet has no atmosphere. So the thing that I've been focusing on recently has to do with transmission spectroscopy, but it's an effect that is not due to the atmosphere of the planet. So I like to think of the word contrast, and the moon is a good example for me. You look at these pictures and you contrast the moon when it's high in the sky to when the moon is near the horizon. You think, oh wow, moon looks really big when it's on the horizon. It looks huge, right? But most of you probably know, right? The moon hasn't changed distance. It's the same size in the sky as it is on the horizon is when it's overhead. The reason is because you're comparing it to something, you have some point of reference when it's near the horizon. You don't have that when it's high overhead. It looks like it's lost in the sky. So what I'm studying is what we call the contrast effect. And what happens is when a planet is in transit, it's blocking some of the light from the star. If the star is homogeneous and there aren't any spots or active regions on it, you're going to see the exact same spectrum in transit as you would out of transit if the planet has no atmosphere. If the planet has a bunch of these features on it, remember I mentioned earlier that these features have different spectra than the rest of the surface of the star. Then when the planet is in transit, depending on which portion of the surface it's blocking, you're going to measure different amounts of each of the spectra. So this is the contrast effect because you're contrasting the surface that's being blocked with the surface that's not being blocked when it's out of transit. So it's a little weird, but I'll show you some examples and you'll see what I mean. I got some videos that are much easier to look at. So that's the question, is can the contrast effect mimic these absorption signatures in the atmospheres of these planets? To put it in more frank terms, are we actually seeing the planet, or are we really just probing the surface of the star? Because if we're not seeing the planet, we're not doing exoplanet science, right? We're doing stellar spectroscopy, which is interesting. You might be able to do some cool mapping of the stellar surface, but it doesn't tell us anything about the planet. So these are some transmission spectra. This is actually data that I took and that we've published in papers. This is that H alpha line that I showed you, but for a different star. This is HD 189733b. It's a very, very fancy name. It's a hot Jupiter that transits an active K star. So this is a star that is not as hot as the sun, but it's much more active. It has much stronger emission in a lot of these lines that we use as activity indicators. These are two different epochs. And what this is the ratio of the in-transit spectrum to the out-of-transit spectrum. And these are mean transit profiles. So we took a bunch of in-transit measurements, we added them all together, took a bunch of out-of-transit measurements, added those together, and then divided them. And this is what you get. You get something that looks like a spectral line. You can model this, and you can come up with physical parameters for the atmosphere of the planet. And it works pretty well, and they match the line profiles that we see. But if you look at the sun in H alpha, and you look at other stars in H alpha is a very strong activity indicator. It has a lot of activity in the chromosphere. It changes over time, a lot of variability. So you have to consider whether or not what you're seeing is actually the planet. It might just be the star. So that's what I've been working on. And the image on the right is something that's going to be a part of the animations I'll show you. What we do is we use a computer and we model the surface of the star. We take all these different types of features, the spots, the bright active regions, and that brown thing in the middle is a filament. These are dark regions on the surface of the star that are kind of hanging above the photosphere. And we put these on a star, and we let our planet, without an atmosphere, we let it transit, let it go across, and we see how the signal that we observe changes as a function of time as the planet transits. And other things that are included, all these are secondary effects. The star rotates, right? So a portion of the star is moving towards you, and a portion is moving away from you. And this changes the relative position of the spectral lines. So you have to include that because it can change the shape of the spectrum that you're seeing.
Because of a Doppler shift.
Right, these are Doppler shifts in the lines. One thing, if you're a solar guy like Franco, probably know that on the surface of the sun, you have all these little motions that are on the order of meters per second. These little cells that are rising towards the surface and falling back down. These also cause little changes in the spectral shape, but they're so small that we don't include them here. They don't have an effect on our observations. But people who do the detection, they do model that. All right, so bear with me, because this is important for the animation, so we'll go through this real quick. But I want to show you some more spectra and explain to you what we're actually looking at. So, as I mentioned earlier, each of the different features has a different H alpha spectrum, or a different spectrum in general, but we're looking specifically at H alpha in this case. So our plage, our faculae, these are the bright emission regions that you see on the surface of the sun. And they fill in the core of the line with emission. So you see the normal stellar spectrum, and then you throw in more light, and you get something that looks like this purple line. The photosphere, this is just a model, is the yellow line. That's what our normal surface looks like. The brown line is a spot. So we not only get less flux from the spot because it's cooler, so it's fainter, but you also get a difference in how strong the H alpha line is, mainly because it's cooler. And you get a lot of other extra stuff because there are different abundances of metals in these spots compared to the sun and the temperature. And then the filament is this big, deep blue spectrum. It absorbs more light from the star because it's basically sitting on top of the star. You can think of the filaments as transiting the surface of the star. So those are the components of the model. So everywhere you see one of these bright regions, we put this type of spectrum, and so on. And what we do in the yeah.
The notch is due to hydrogen alpha being absorbed,
Yes.
but doesn't the sun emit a lot of hydrogen alpha?
It does in the chromosphere, but in the photosphere, it's being absorbed. Yeah. So the chromosphere
Okay.
is the layer, the hot layer on top of the photosphere. And so you basically get two spectra. You get one from the cooler layers, and then over that, you get emission lines from the chromosphere. Does that make sense?
Yeah.
Sure. Okay. Let me, all right. Pause it when we get to the actual thing. Okay. So this is an animation of our hot Jupiter, and it's going to transit this piece of the star down here. And it's going to go across a bunch of these different features. We've got our spots, our plage and facular regions. I don't put any filaments in because it turns out they don't really have much of an effect on the spectrum, so we don't include them. On the right, you can watch a few different things. On the top, those are our transmission spectra that we measured. That's our data in the gray lines. The red line is the model. So this is what we're trying to make reproduce the data lines. The bottom is a time series. So this is a function of time as the planet transits. We can actually make individual measurements of these lines on the top, and that's what these points are. It's basically a light curve. So it's how bright or how much absorption we're getting as a function of time. And you'll see that change as the planet transits. So you can see there's a lot of spots, but this is really only about 3% of the surface of the star. And the active regions cover a little bit more, maybe like 5%. So let's watch it go across and see what happens. So you can see the line change a little bit. We get a little bit of absorption. Depends on what it's covering. And we get to the end as it gets off the star. What do you notice?
It's small.
Small.
Yeah.
Very small effect, right? We didn't get the absorption that we observed. So this is a hint that we either need a lot more of this stuff, or we need to change the properties of the spectra that make up the spots and active regions. Let's look at another one. So in this case, we've blasted up the active region coverage, right? This is like 20% of the star is covered in, or I can't remember, it's something like 15% of the star is covered in active regions. A huge amount of stuff. And it's centered, these bands, remember we talked about these latitudinal bands of activity, are centered almost directly, yeah, on the path of the planet transit, exactly.
But your planet is in the same spot as the last time, too.
Yes, it goes across the same chord every time. Yep. So we can put these wherever we want to try to reproduce our observations.
And then, by the way, the velocity on the x-axis is related to its radial velocity?
Are you talking about this?
Yeah, that velocity.
This, yes, you can think of this as radial velocity, although it changes depending on which piece of the star you're looking at. So you can also think of this as wavelength. So this is the center of the line, and this is the red portion of the line and the blue portion of the line. We've got it in velocity space because we tend to, it's easier to think about motions in terms of velocity rather than wavelength. So let's watch this guy transit. And the other thing we've done here, I didn't mention this, we jacked up the strength of the emission spectra for these bright regions. So remember the purple spectrum where we had the filling in of the core? That's much stronger in this case than it was in the last case. So we've done two things. Jacked up the surface coverage and jacked up the strength of the emission. And you will immediately notice a huge difference, right? All of a sudden, we're reproducing our observations. Not perfectly, but we're able to reproduce an order of magnitude effect, which in this case is pretty good because the observations are far from perfect. They're pretty low signal to noise. So we reproduced the light curves, not both of them, and certainly not with the known configuration. I'm sure it doesn't look exactly like this. We're making a lot of approximations here. But this is suggestive. If we can do this, it means maybe what we're observing is not the planet. Let's look at one more. And this time I've taken a very similar distribution as the last time, except instead of centering it on the planet transit chord, we've shifted it towards the equator of the star. So now the planet is not going to transit as dense of an active region coverage as it was before. Let's see what happens.
Not quite.
A little bit. Oh, there goes. Not so good, right? We don't have a consistent transit. But one thing maybe you noticed is this is kind of arbitrary, right? Like what if we moved a few of these active regions here to make it so we didn't get that big gap
Right,
in the
because
middle?
we're stacked,
Yeah,
stacked in one spot of the star.
right. That is what we don't know. We do not know what this distribution of active regions is. This is very exploratory. We're trying to see if we can reproduce what we see with this type of stuff. And I think we can, although we really need to know how strong the emission is from these active regions. That's another thing we don't know. Remember, we get that integrated light from the whole star. On the sun, you can look at these individual pieces and say, oh, the spectrum looks like that there, it looks like that there, and it looks like that there. We can't do that with other stars, so we have to throw in guesses and see what we need to reproduce our observations. But so far, what we need is not out of bounds physically. None of the parameters I've chosen for these models are unphysical, right? So what we're currently doing is we're trying to do the same thing for what we call a super Earth, and this is 55 Cancri E. It's an illustration on the bottom, shows you its relative size to Earth. HD 189, the star I just showed you the animations for, is about 10 times the size of Earth. This is only about 2 to 3 times. This planet orbits less than, its orbital period is less than a day. So it goes around its star, its year is 0.7 days long. It's pretty amazing. It's super hot, but there were some suggestions that it has an atmosphere. Despite being so close to a star, there were suggestions that there is still gas bound to this planet. So we went out and we tried to measure it. And this is the preliminary results. So you guys are the first people outside of my research group at Wesleyan who have seen this. And this is calcium-2. So this is a strong metal line that we see in most stars. But again, it's a strong activity indicator in the chromosphere of stars. Whenever we look at a star, we usually see some emission in the core of these lines, suggesting that we have a lot of these active regions. 55 Cancri is not a very active star. It's more active than the sun. It's less active than 189, which I just showed you. So the next question in my project is to answer whether or not we can reproduce this calcium-2 signal we see with the transit effect, the contrast effect, sorry. My prediction is we will be able to. It's a pretty small signal, and it doesn't move in velocity space like you would expect it to if it was from the planet. So it might be due to the star. But this is important because this is a pretty big area of research right now. People are trying to measure the atmospheres of these planets, and if we're not actually looking at the planet's atmosphere, it's bust. You're not doing exoplanet science. So we need to develop these a little more.
And
All right.
these planets, by the way, they have atmospheres because they have a solid core. It's massive enough.
Yes.
To be able to retain?
Yes.
So they're actually a very large, solid core.
Yes, so 55 Cancri, I can't remember the mass, something like 2 times the mass of Earth, and 2 times the, or 3 times the mass, 2 times the radius, or something like that. So the surface gravity is like 3 times stronger than Earth. So it actually holds on to stuff better than Earth does. All right, so I'll finish up and we'll some take-home points. You don't know your exoplanet unless you know the star that it's orbiting. And that's true for characterization, detection, and these more detailed things like trying to measure the atmosphere. We can mimic these transmission signals with stellar activity, and we need to know more about this or we're not measuring the planet. And this is sort of the beginning, so stay tuned. These are not a lot of people are doing this, so it's not super hot. We're not trying to measure life in the atmospheres of Earth-like planets, so we don't get a lot of press, but that's why I'm really happy you guys are listening to me. I think my wife is sick of hearing about it. And so that's it, and I'll leave you with another beautiful SEO video, because this is from 2 days ago, I think. And I think, yeah, you see some bright little flaring regions and huge coronal hole. If you watch this, it actually starts to close up.
Yep.
Oh, now come back.
Closed up.
Right here.
Did you do that again? Did it kind of fade away?
Yeah, just like,
That is the weirdest thing.
Something's on, something's on his.
I don't have an answer for you.
I guess he's done.
It's not this
I'm
one.
done anyway.
Try it again.
2 questions. One is, while the planet is losing its mass as it's orbiting, because you're losing mass, you're going to have orbital period changes. Because you don't have the same mass anymore. So now your observations change with the next orbit.
Almost.
Almost,
So
okay.
the orbital period only depends on the mass of the star. So the
Okay,
planet can
right, because
right.
of the big difference between.
Yes,
right,
huge.
okay.
Yeah, the planets are much less mass. But you're right. So if it was a binary star system,
Okay.
absolutely. Yep.
Okay.
But that actually, your observations do change because any of the material you're losing can stay in the orbit.
Okay.
So you could be looking through different material every time you look at a transit.
And the second question was that you talked about the surface of the star changing in meters per second.
Mhm.
You are observing this change in stars that are thousands of light years away, in which we have a relative motion change as well, on top of the Earth moving, on top of the solar system moving, and you're able to tell that you've only got a 3-meter change?
I do not tell that. I cannot do that. The most sensitive radio velocity surveys right now are getting down to tens of centimeters per second.
Relative on the star with all of the relative motion involved.
Relative velocities of tens of centimeters per second. So, like the star's doing this, and they're watching it do that. It's unbelievable. It's amazing.
Okay.
Yep.
All right.
And they have lots of calibration techniques, and it's a whole field in and of itself. Students do their PhDs developing
The instruments.
code to even
Oh.
do it. I mean, it's tiny things.
Okay.
When you say the planets are super hot, can you measure emissions from the planets, and can you tell when the planet goes behind the star?
Yes, absolutely. So, what I do with the transmission spectroscopy, you can't, because there's no transmission if you don't have any blockage. But people use things like the Spitzer Space Telescope and the Hubble Space Telescope, and they actually watch the planet get occulted by the star. And you see a change in the light curve because the planet's so hot, it's actually emitting a relatively large fraction of the system light. Like upwards of a few tenths of a % or something. And you can measure that. So yeah, and you see a bump, which is the increase of the planet's emission being beamed towards you, because now you're seeing the hot side, and a transit in the bump when the planet goes behind the star. A secondary transit, so it's called. Yeah.
Well, we were talking about the solar winds and how the solar flares and the heat off of the planets and the sun. And it just, what you said as far as Mars, Well, couldn't that be happening to Earth, like global warming?
Not in that case, but we are losing atmosphere to the solar wind. It's a little bit.
So I would think that's all part of the cycle.
It absolutely is. It's certainly part of it. Yep. And
Magnetic field though, too.
we do have a magnetic field, although I'll mention there's been a lot more debate in the planetary science community about whether or not magnetic field's actually that important.
Correct.
It might not be. A lot of people still think it is, and I tend to be in that camp. But we do get a lot of charged particles from the sun, and they hit the Earth's magnetic field, and they get funneled down into our atmosphere. So there is some interplay there. Yeah. But in terms of heating, it's pretty minimal.
Looks like you're developing new criterion for like this analysis of planets, transits, and everything. What about everything that is being confirmed before this 3000? They didn't take into consideration what you're studying now. I mean, this is all new stuff.
A lot of the stuff I'm talking about is like a second order effect. So you can still say we've detected a planet, but the properties of the planet might be a little bit different. Yeah.
So it's more of a detailed analysis.
It's more in the weeds. Yeah. That like your transit might be affected by a star spot crossing, but you're still seeing a transit, and you can say you're seeing about 1% of the light being blocked. Yeah. So that tends to be where you go, right? You do the first order thing, you see transits or RV signals, and then you say, oh, but we're seeing this other thing, so let's go figure out what this is. And you see little other things, and you go do those. So that's how it works. Yeah.
So you said that they can detect mass loss of the planet. What type of resolution do they get out of that?
So spatial resolution, none at all, except in time, because we know pretty precisely based on the orbital parameters of the planet, we know where it's going to be at any time. So when we observe the star, we know where the planet is. And based on the signature that you see, you can try to reproduce how the planet is losing the mass. But we don't actually take images of it. These are all spectra. Yeah. So it's all integrated light from the star. Thank you guys. You threw a lot at you, and I'm really happy that we're having a good conversation.
That's good.
Yeah.
What about,
Oh,
sorry.
got one more?
Yeah. Do you build the spectroscopes you work with?
Nope, I do not. I have zero instrument building experience.
Are you using the spectroscopes in space, or are you using the ones down on the ground for your observations?
The main spectrographs that I use are on the Keck telescopes and at a telescope in West Texas at the McDonald Observatory. Yeah.
But I mean, the sun has got like a 11-year cycle approximately. What about, do we know anything about the cycles of other stars?
Yeah, absolutely. Proxima Centauri b, I think, has been monitored for almost 2 decades now, and they have a pretty good idea of what the the stellar cycle is. I don't remember how long it is, but they do see similar patterns. Yeah.
So, I mean, if there's low activity, then you actually have a better chance of detecting planets, right?
Yes. Yeah, you don't get as much contamination in the signal. Yep. So they do go out and they look at low activity stars because they're higher probability that you can detect some. Yeah. But if we're going to detect planets like Earth, you're going to have to filter out a lot of this noise, which is what people are trying to develop really sophisticated tools to get down to the meter per second level. Or sorry, centimeter per second level, not meters. Yeah. But we'll see. Might be impossible to do that.
Very interesting.
Yeah.
There it is.
All right. Thank you very much.